and let me know when we are live.
Put off your mobiles. All right, 11 o'clock and time for another Chai and Wai. Welcome to a Chai and Wai on a rainy day.
Thank you all for coming on a rainy day.
And today's speaker perhaps doesn't need any introduction, but for formality, I'll introduce him.
I'm me.
Okay. So speaker is Professor Arnab Bhattacharya. Today he's going to talk about some physics related to the sports. I may add that he's not a professional sportsman, he's an amateur sportsman. And before joining TIFR, he did his BTech in engineering physics from IIT Bombay and PhD at University of Wisconsin in US. And now he's going to tell us about what excites him about Olympics. So all yours.
Okay, and welcome to the online audience as well. I hope we have people online. Please remember, if you're online, there are two things to remember. One, the only way you can communicate with us is through the chat. So please keep your questions and comments and all coming on the chat. Ulhas, who just introduced me, will be monitoring the chat, and he can ask me those questions during the thing. I will also ask you some things in the middle, which I may want you to put on the chat. The second more important thing perhaps is, if you're watching online, you don't get chai. Okay, so with that, let's get started. Are you all watching the Olympics?
Yes.
Awesome. Okay, so my plan is to look at the Olympics and see if there is something we can do about connecting it to some science. And for today, we are looking mostly at what I would call physics. Okay, so I'll explain this in a bit. Okay, so by the way, these are, every Olympics has little symbols that they use for their games, and you can see a pictogram. These are from the 2000. These look like old tablets. So this was the 2004 Athens Games, 100 years thing. So this was, they have made it in the old style. So every and you can just Google and you'll find a list of the pictograms of all the modern Olympics that they've had. So I just like these. Okay, so now, you know, the Olympics, you're watching sports, you're watching the best athletes in the world. They're doing some unbelievable stuff. They're running fast, they are throwing far, they are, you know, jumping around, whatever they're doing. Okay, I need to start screen share. Ah, ha, ha, ha. See, thank you, sorry, let's go back. Screen share, sorry about that. See, you should remind me of such things. No, normally I'm the guy reminding. So screen share. Yeah, just a second. I need to hide floating meeting controls. Okay, a very quick beginning again for the online audience who missed it. What you see on top of your screen are the pictograms from the 2004 Olympics. Every Olympic has had its own pictograms. You can Google and find the whole list of them till Paris. And okay, so, you know, you've been watching things at the Olympics where people are running incredibly fast. What? I'm sharing my Zoom screen. I just need to kill this. I need to kill it. I need to minimize this and get this out of the way. That's probably good. But that doesn't show up on the... okay, so, you know, what's physics got to do with it? We'll get there. Okay, so this is a good excuse to talk about science. Now, let me give you the disclaimer. Don't believe what he said. I am not an expert in any sport, okay, or on the physics of sports, or the types of materials used in sport equipment, etc. Yes, I walk a lot. I walk long. I can finish a marathon. I finished several of them, but that's okay. So long distance running, maybe a little bit, but otherwise nothing else. Most of what you're going to hear is based on some interesting observations at the ongoing games. Much more, I mean, these are still going on. Much more on the 2020 games in Tokyo, which were held in 2021, and the earlier ones, of course. And you may see a lot of, you know, manufacturers, very famous sports manufacturers, things, but I'm not endorsing anybody here. I'm not discussing ball sports today. We've had some sessions over the, you know, football World Cup and all, how balls curve and bend and all. There's a lot of stuff happening with when there are, but we won't discuss ball sports. That's a different talk. Also, I'm not so much into materials, science, chemistry, etc. I've done one of these about 4 years back or 8 years. One of the Olympics we had done this, material science. So today it's mostly physics. Okay. I've copied images from the internet. I've tried to put references wherever I could. In some places, perhaps I've missed it. Okay. So again, a little knowledge is a dangerous thing. You know that. So with that, let's go ahead. Why physics? Okay. Now, physics deals with everything in the universe, right from tiny little particles, electrons, protons, etc., to the movement of galaxies, on the other extreme. When objects move, why do things move? What influences their motion? That is all physics. And physics involve forces, momentum, there is gravity pulling you down, there's a torque if you are seeing something, if something's moving through the air or water, there's going to be aerodynamics or hydrodynamics. That's all part of physics. The other thing in physics is there are things called conservation laws. For example, energy. Energy, you will go from potential energy to kinetic energy. You will generally not lose energy too much. Similarly, there's something called angular momentum. Maybe you've not heard of it, but if you're spinning around, there is something that's conserved. You cannot change it very easily unless you apply some external thing. So there are all these things in physics which are relevant for sports. Okay. So physics deals with stuff that is moving. And at the Olympics, there are a lot of things that are moving. So either are humans moving. They could be walking, 50-kilometer walk, one of the longest events. They could be running, whether it's a 100-meter race or a marathon. They could be jumping, high jump, long jump, whatever. There could be humans on horses who are doing stuff. Won't talk about that. Then there are a category of sports where you throw something. It could be a stick-like thing, which is a javelin. It could be a heavy ball, which is a shot put. It could be a discus, disc. So you can throw things. Then you can propel things. I can stretch a string, put an arrow to it and leave it, and I can let the arrow fly. So I'm not throwing the arrow, I'm propelling the arrow. I can shoot with a gun and I have a bullet that goes somewhere. Okay, you can row a boat, you can have the wind push you. So there are things which are being propelled. That's a third kind of motion. And of course, there's a combination of all of this. If you're playing hockey or football or something, you are moving, you're propelling things, you're hitting the things, all that, everything is coming in. So there is a lot of motion in the Olympics, lot of things which are moving, and hence there's a lot of physics. Now, most of the elite athletes, they don't necessarily know all the equations that are there in the background, etc. They don't need to know all this. But at the top level, every one of those athletes understands somehow, intuitively or otherwise, or through training or what else, they understand the physics concepts that are involved in the motion of either themselves or whatever they are throwing or something. Of course, there is always exceptions to prove the rule. So there are outliers. So she's competing this year as well. This is Anna Kiesenhofer, one of my heroes. She was one of the surprises of the last 2020 games. She is a postdoc in mathematics. She works on something called B-symplectic functions, which I don't know what they are, but essentially she solves partial differential equations. But she's also a cyclist, and nobody thought that she was in any competition for a medal. She was Austria's only athlete at the games in the cycling race. Okay, I mean, not in the games, at the cycling race. And when they started, this is one of the longest, 137 kilometers is one of the longest races in the Olympics. So when she started, nobody took her seriously, and she just started from the scratch. Now, normally people don't do that. They go in a group. In cycling, it's called a peloton, and then at the end of it, they sort of break away and do something. She just went, and the people who thought, the good teams and all, they ignored her. They didn't even know she was ahead, and she happened to be ahead for the whole race, and she was alone, and she won the race. So this is one of the most amazing things, and she uses a lot of mathematics and things and all to analyze her own thing, but she's a mathematician. Okay, but these are the exceptions. And because of what has happened, thanks to this, since we are on cycling, just remember now, because of the inputs we have, everything you see is extremely controlled. So in a cycle, for example, what are the allowed sizes? What are the allowed angles at various parts? How high, if your rider is of a certain height, how high can various things be? Everything is controlled by the Olympic Committee. There are lots and lots and lots of rules. Okay, it's not that you can just go and do what you want. Okay. Let's step back and look at things a little historically. Okay. In the last 100 years, there has been a huge improvement in performance. Okay, some of it is quite dramatic. So look at the pole vault. In 1896, you could get the gold by jumping 3.3 meters. In 2012, the qualifying was 5.72. The 2024 qualifying is 5.82 meters. The world record, Duplantis, is 6.24. Hopefully he'll break it. Maybe he'll break it. Who knows? So there is something called an improvement index. We won't worry about what it is, but just remember it's gone up by a large amount. Okay. The person who won gold wouldn't even qualify. Okay. Now, if you want to see the qualifying numbers, it's available on Wikipedia. You can check it. The entry standards, which you must demonstrate in 2023 so that you can compete in 2024. And this just tells you how hard it is to get in. Okay, 100 meters, for men, you have to be at least 10 seconds or below. For the marathon, you have to be 2 hours, 8 minutes. Okay, nobody from India qualifies for this. Okay, for 10 kilometers, you should be able to run 10 kilometers in 27 minutes to qualify. Okay, all right. 20-kilometer walk is 1 hour, 20 minutes. Okay, so please remember, any Indian who has reached the Olympics has managed to qualify. Don't worry if they get a medal or no medal or whatever. Let's not, just remember, being able to meet the Olympic qualification target itself is amazing. Amazing. Please do not say, oh yaar, fourth aa gayi, kya kar rahi hai, khelna nahi aata. It's terrible. If they have qualified for the Olympics, they have met some amazing standards. Okay, just remember this, please. Okay, 100 meters, as we just saw, in 1900, you could win the gold medal at 10.8. In 2012, it was 9.63. Very famous. Qualifying at that time was 10.18. Today, it's 10. Okay. Cycling in the 1 hour time trial, it was in 1894 in 1 hour, people went 38 kilometers. 1996, 56 kilometers. The improvement index is 221. Now, why is this huge? Because remember, in most sports, whether you're running or cycling, the faster you go, there is air resistance, which goes as a square of your speed. So if you double your speed, the resistance is 4 times more. Okay, so it's much more harder in cycling to go faster. So which is why the improvement index is though the distance may have just doubled or something, the improvement is much more than that. Javelin is a very interesting one. In javelin, in 1908 was 53 meters. The world record under the old rules was 104 meters. In the new rules, is 98 meters. Improvement of something. 2024 qualifying is 85 meters. Okay. Just remember our hero, Neeraj Chopra. You've heard of Neeraj Chopra? When he first came on the scene in the 2012 Junior Nationals, he got the gold medal and he broke the Indian junior record. At that time, the record is 68 meters. Okay. Today, you need 85 to qualify. Of course, he's there. I mean, he's going to be there on the 8th. I hope. He's one of our gold hopes, actually. Okay. Now, is this physique? Is it training? Is it equipment? What is something? Just remember that most of this improvement that you're seeing is not due to understanding physics. Okay. It's not due to high-tech materials. It's not due to fancy sensors, all that. They have a role to play, but most of it is not due to that. Most of our improvement is because of various socio-economic factors. We have much more time these days. We have leisure time. There are much more professional sports organizations, training schedules, all that. The government supports various sports things. There are things to find out talent at a young age and nurture them. Okay. Our food is much better. You can get high protein diets or whatever you need. Coaching is much better. Medicine has improved. If you're an athlete, you will fall and maybe hurt yourself, break a leg, whatever happens. Recovery is faster. More women are participating in sports. There are lots of things which are not physics. So it's not only physics. Please remember, it's not only physics. Okay. All right. Now let's look at this. How much of this performance? Now, see, the best person in the world, might be some superstar. Like Michael Phelps has a massive handspan, etc. Usain Bolt had something really remarkable that he was able to run at the speed he did. So it's not fair to compare the best performance because that person might really be an outlier. Okay. So, but the person who's the 10th best in the world is certainly very, very good. Right? The 10th best person. So it's much better to compare the 10th best person. That's more like the typical elite performance. And if you see the typical elite performance, this is the time taken to run 200 meters, the winning time. Okay, typically the 10th best person, as from 1900 to over 100 years. Now you can see the time is slowly dropping. People are running faster. And remember, I told you it's the amount of time you have. You can see these bumps due to World War I and World War II. If there's a world war going on, your focus is not going to be on sports. It's on something else. So naturally, sports goes down, and you can see the blip in the performance, right? Yes, this is running, where you want to come as fast as possible. Look at long jump. Long jump, again, the distance people are jumping is increasing, and you can see these dips due to World War I and World War II. Okay, socioeconomics, very, very important. Look at shot put, the distance you are throwing. Okay, and again, look at the slope for women is higher, because women start later, but there is a lot of support, so they are improving faster. But again, you see these dips due to World War I and World War II. Okay, now if you noticed very carefully, yes, performance is improving, but it looks like it has flattened out at the top. What happened? Right, we improved, and then have we reached a limit that we can't perform any better? Are we really reaching the limits of human performance? If you're online, please put your answers on the chat. Let me see if here somebody wants to say, why do you think we have flattened out? Anyone taking a guess? Yes? The potential is at its highest, okay? Tough to do any better. Okay, I'll give you okay, let me take one more and then I'll give you a hint. Any online things? Or they are delayed by a bit? Are people there online? Okay. Yes, person in yellow. Okay, maybe I should give you a hint. I'll give you a hint. It's not connected with today's topic. I discussed this in detail in the chemistry of the Olympics part of it. And if you really want another hint, remember this guy called Hans Gunnar Lienwag. Absolutely. So this point is when dope checking became compulsory at the Olympics or at elite sporting events. Okay. So this slope that you see is not a natural slope as you in a way, because what was happening. So by the way, this Hans Gunnar Lienwag was the first person who got a medal. He was responsible for the entire Swedish team's medal being rescinded, caught for doping. And what did he use? What did he do? He drank 2 beers before the event because he wanted to. And because of that, his entire country lost the medal. Okay, but there have been doping has been around in sport forever. 1904 marathon, this guy is trying to run. In the middle of the race, they came and gave him a shot. Okay, of course, there was a lot of state-sponsored systemic doping in the erstwhile East Germany, right? Then the famous case of Ben Johnson and the 100 meters run in '84. So eventually, drugs are getting more and more sophisticated, and you can mask them and this and that, and there is you can do blood doping. Okay, sorry, and it's not just things. You can even have. Oops, what happened? Even horses have been banned for doping, because even horses, you don't have to drug the rider. You can drug the horse. So even horses have to be in equestrian. Even horses are subject to doping checks. Okay. Yes. No, you can eat, the horse should not. It's a horse. It's for the horse, not for you. So what is the dopant for you and what is the dopant for the horse are different things. Okay, let's not get into this. We're not getting into this. We're going back to physics. Okay. So the main thing is, you saw that thing flattening off. That's because that's when doping checks were introduced. After that, the slope has really gone down. So let's look at a few different sports. And I'm going to start with javelin. Okay, why? Because, hey, that's one of the rare sports in which we've got a gold medal. You recognize this person? Good. What did he do? Good. Do you recognize these two people? No. Please remember, there are many different, along with every Olympic Games, there is a Paralympics Games. Okay. And way before Neeraj Chopra, Devendra Jhajaria, he got the gold medal at the Paralympics in 2004 and 2016 in a category. So this F46 is field events for category 46 for amputated people, upper limb amputation. This is Sunil until he got it in Tokyo 2020 gold medal for lower limb amputation. So we have got gold medals in javelin before at the Paralympics. Please do not forget, there is an entire set of games for the Paralympics, called the Paralympics, which are held. They will be held from August 28th onwards. Once this one ends, this game starts. Okay. All right. So no, I thought it's, everybody's heard of this, but we've had athletes representing India at the highest level before. So now let's look at the same curve for javelin, which looks very different. Okay. So now, of course, you see that dip due to the war and all. But then you see here there is a sudden improvement because of something called the aerodynamic javelin. And then you see there is a sudden decrease as well in 1986 or something like this. I'm coming to it. So the javelin is the only sport where the rules were changed to limit the performance, to bring it down. And let me explain. Okay. So please feel free to ask me questions. Okay, we don't have to finish everything. If there are online questions, please let me know. So what is a javelin? It's basically a stick. You throw it with one hand, right? You've seen the javelin. You guys have heard of javelin. You've seen this something. Okay. So naturally, a lighter stick will be easy to throw far. So the rules say that there is a minimum weight for a javelin. So it's 800 grams for men, 600 grams for women. That's the minimum weight of your javelin. It cannot be lighter than that. So far, so good. Now, earlier, the javelin was made of wood. Later, people went on to make it out of steel, aluminium, carbon fiber, etc. Now, earlier, what did people think? They thought that if I make it pointy, like a needle, it will be going through the air quicker. There'll be less resistance. So you want to minimize this drag, aerodynamic resistance, and hence it will fly faster. But then there is another thing. Anything which you throw is going to vibrate. So if it's very flexible, it will also start vibrating. So you want to make it stiff. So then they tried to make it stiff. Then they figured out in the 1950s, hey, wait, we can do better. There's nothing, it's only saying weight. It's not saying anything about the shape of the javelin. So instead of making it a round stick, which is pointy, I will make it something like this. Okay, which is flat at the bottom, whose curvature I can change. So it's like a wing, which will get some lift, and hence it will fly further. Okay, like a plane wing, exactly. Yes. Cross section means if I have this rod, if I cut it, what is the area that you see? Will you see a circle, or will you see a triangle, or will you see what it is? Okay, so that's the cross section, the area when you cut it. So now the problem because of this is, as the people are designing these fancy javelins, they are flying far, and the world record is coming to almost 100 meters. Now the problem with this are two things. Remember, Olympics is designed to be watched on TV. Right? Most people are watching it on TV. If the throw is good, and 100 meters is approximately the length you have in the stadium, right? Maybe a little bit more, but not too much more. Okay. So if it goes beyond 100 meters, it's not going to fit in your stadium. It's going to be difficult to get it on TV. Practical issues, paisa nahi milega. But the other problem is, just see, I throw something. Ideally, if I throw something, it should go up and come down. But if it's going like a wing, it will go this way, and when it lands, it's landing like this. So these are called flat throws. Okay, if it lands like this, where did it land? Here or here? See, if it lands like this, it's very easy to say where it landed. If it's like this, it's a flat throw, very difficult to say where it landed. So there was some controversy in that. Yes. One could design rules, but the problem is it's getting beyond 100 meters. Okay. So then they decided to do something about it. So let us watch the old world record throw. This will never be beaten because now the rules have changed. You cannot throw like this. Okay. This is a guy called Uwe Hohn from East Germany, who, by the way, was Neeraj Chopra's coach. Okay. So just watch the throw. Okay, it's thrown. You'll see it from different angles as well. So here he is. This is the record. Watch how it lands. Okay, there he throws it, manages to stop before the line, and see, it's almost going flat. Okay, and then it landed somewhere, and people are running to it. Okay, now let's just remember how this throw looked, because I'll show you the new throw also. Okay. So the physics of the javelin is very complex. It's very, very complex. So what is happening? You have something in the air, right? So there is gravity which is going to try and pull it down. There is somewhere, because it's going through the air, there is a lift factor on it. Somewhere it's going to get pushed up. There is air resistance. It's at an angle. So there are lots and lots of forces in it. And many things matter. At what speed do you leave it? At what angle do you leave it? Okay, you know, when they say that, for those of you in college and you've heard of this thing, that if you want maximum range, you throw something at 45 degrees. That's for a ball, a point object, not for a stick. And not for it, that's in vacuum probably, not in air. If there's air resistance, all these things will change. Okay, how do you leave it? At what point do you leave it? Right, and then the angle at which you give it, the wind direction, lots of things are going to affect this. The most important is what is called the location of center of gravity and center of pressure. I'll explain that in a bit. And of course, it depends on, you know, the air temperature, density, all these things matter. Remember, it's a millimeter that's going to separate the winner. So all these things matter. Now, what did they do? They ensured, they made only one change. The change, they said that the center of gravity should always be ahead of the center of pressure. So the center of pressure is where the javelin is being pushed up. The center of gravity is where the gravity is pulling it down. Now the center, remember, it's flying this way. If your center of gravity is ahead, it will always dip down. So at all points, if the center of gravity is ahead, the javelin will always dip downwards. That's the change they made. And after this, obviously the things came down. Then, I mean, immediately came down. Then again, people improved their technique and all, and they went. Okay? So now, watch the throw. Watch this one. Okay, this is of course the famous throw. And woo, what a stop! But look at how it is going, and it's dipping, and see the way it landed. Very different than the earlier one. So here they changed the rules so that you would not have. That's the same thing in slow motion, and that stop is amazing. And there it lands, and you've cleared that 85 meter. That was the thing. Okay, so this is. Center of mass is where the center of gravity is acting at the center of mass of the object. For some objects, yes, but in this case, you can assume that the center of mass is the center of gravity. Okay, it's just gravity acting at the center of mass. Yes. So the first throw I showed you, the question was what were the two throws? The first throw was Uwe Hohn, 104 meters, 104 point something, and this was Neeraj Chopra at 2020, which was 88 or something of that, something between 85 and 90. No, you have to submit your javelin for approval, and they know exactly where they can figure out where the so in general, during the flight, the javelin should be dipping all the time. That will happen if your center of gravity is something, and that, see, most of the standard people use standard javelins made by a standard manufacturer who will have done wind tunnel testing to tell you where exactly is the center of pressure and the center of gravity. So these will be known factors for a given javelin. How is the center of pressure determined? Well, you put it in a wind tunnel and you see at which point you get lift. By the angle, if you put it in I balance it in a wind tunnel, I let the wind flow, right? It will balance itself at some angle. And I know where the center of mass is, and I know what the angle is. I can figure out where is the force acting upwards at which point. Yeah. So people will do all those things, but yeah. They are not rounded. Most things are, they're not perfectly round. Okay. They bring their own javelins. Do the players bring their own javelins? They bring their own javelins. Yes.
We can also observe in the first throw it was at 45 degrees, but now when we see it's not going at 45, like around 50.
Yeah, it's not 45. Okay, let's move on. Archery. There's something where typically another thing where we tend to do well. Okay. So today's, all of us when we were small, we must have taken a bamboo thing and tied a string to it and played some Ramayana or whatever else, right? Now that's a very different than the modern bow. Most of the events in archery will be some version of what is called a recurve bow. What is a recurve bow? A bow is curved, but you notice this bow curves this way and then curves that way. Okay, the curves, so there is a main curve and then it curves outward, so it's recurved. That's a recurve bow. Okay, again, one of our best athletes is Sheetal Devi. Last 2022, she won 2 golds and 1 silver at the Asian Paralympics. She's competing this year as well. She is the only athlete to compete in a Paralympic with no upper limbs, archery with no upper limbs. Okay, which is absolutely amazing. She just manages it with her toes and her teeth to hold the thing and do it. Okay. Now, they say that something flies as straight as an arrow. Okay. I want to tell you one thing, that the arrow does not fly straight. Okay. Believe me, the arrow does not fly straight. There are 2 issues. One is that the arrow itself moves. There are the arrow's vibrations, which we will see. So the arrow, if you have a long thing, the arrow is going to move this way and that way, this way and that way. That's one thing. But the other thing is what is called the archer's paradox. Now, unlike bows which were used to hunt prey, which is a crossbow, the bow used to hunt prey. If you look at old things, the bow is not held vertically, it's held horizontally, and you shoot through the thing. Now, remember, you have, just imagine a bow and arrow. You have a bow, you have an arrow. The arrow has to lie at the side of the bow. It's not going to go through the bow. So it has to lie this way. I'm exaggerating. Imagine the bow is so thick. It's not, it's some thick, but it's holdably thick, right? But it's this way. It's not straight. You either have to keep it this way or this way. But your target is ahead. So you want to shoot this way, but it has to hit the target which is ahead. So you can, of course, move it this way. So your bow is, but then you're not pointing at the target. So remember, this is the archer's paradox, that your bow is not straight, and hence the arrow is not directly pointing at the target ahead here. Also, the bow, when it leaves, is going to have these funny bending motions. Okay, I know you don't believe me. Yes, question at the back. Yes, go ahead. Arrow should not fly straight. It does not. Yes. The question is, does the javelin also have these movements? Yes. Of course, the javelin is much thicker, and in fact, they made it, the reason that they moved from wood to steel was to prevent these motions, to make it stiffer, so it would not move like this. But first, guys, just wait. Let me just show you a video of how an arrow leaves the bow. Okay. So the first thing is, remember, the arrow is going to go this way. The string of the bow is going to go. Remember, the arrow is getting bent, no? Energy, I mean, you have to conserve momentum. The string is going to go left, right. Okay, just watch it, the release, the left video. This is high speed thing of an arrow being released. Just look at the string and see how the string moves left, right. Okay, look at the string. You see the arrow bending? And can you see the string moving? The string moved left, right. Okay. Now, when the arrow flies, how does it look? Look at the arrow. Okay. So now do you believe me that the arrow does not fly straight? So, of course, this is at very high speed. You will just see it go whoosh. And you will not see these movements. But these movements are there. Just hang on, let me finish. So remember that you are putting what are you doing here? This is energy. You're stretching the bow. You're putting potential energy into it. You're storing the potential energy in this elastic energy of your bow and the string. You're releasing it. It's going to be transferred into the kinetic energy of your arrow. You want to minimize the energy lost in all of this, for one, and you want to increase the accuracy of you hitting your target. Okay. So these are where the difficulties in archery are. It's not just you can pull a bow and leave it and it's going to hit the target. It's quite difficult. Okay, I see a lot of hands up over here. So maybe we pause over here and take a few questions. Any online questions so far? Okay, tell me. But meanwhile, let's take a question from here. I will reread the question for the audience. Yeah, one of you. Yes, Superman. Let's start with you. That's another thing. Yes, the arrow, you cannot shoot at the same. You have to count for the fact that the arrow is going to go up and gravity is going to put it down. Yes, that's true. The arrow, yeah. So if the arrow is bending, how do you get the accuracy if your arrow is bending and the target is not at the same height and you have to? Well, that's what makes you a elite athlete. No, that is the whole point in your practice, in your preparations. You practice this a million times so that hopefully the day you have to do it for a medal, you'll be able to hit it, and you'll hit 9s and 10s. You get 10 chances or something. You'll not hit 8s and 7s outside. You got to hit the bullseye, and that's all a matter of practice. Practice, practice, practice. Okay, next question. Not anymore. Mostly the arrows are made from steel, some particular alloys of steel designed to minimize these vibrations and all. Also, if you notice, these arrows had little wing-like things at the end, little feather-like things at the end. They are actually meant to, it's called fletching an arrow. It's meant to give it a little spin. You saw the arrow spinning? So maybe you can watch this guy again. See, you'll see the arrow is also spinning. This is spinning. It's actually spinning. Okay. And the spin helps to stabilize the motion as well. So that's the purpose of the feathers at the back, is to ensure your arrow spins when it leaves the thing. Yes, question. So like in the javelin, it's not like when you cut, like when you cut it, it's not a circle. Is it a circle in the arrow, or it's not a circle? Question: what is the cross section of an arrow? It is mostly a circle. Yes, let's take some online questions.
3 connected questions.
Okay.
Firstly, was there any effort made to make a hole at the center of the bow so that the arrow is going right in the same place?
Not for sports archery. In sports archery, it's a standard bow where the arrow is at the side. There have been crossbows designed where the arrow can, with a split bow, so that the arrow can go through the center, but not the standard recurve bow used in archery for sports.
Other 2 questions are how to prevent this, and secondly, connected question: will the arrow wiggle less if it were a crossbow? Which I think you are just answering.
Yes, I mean it depends. You cannot prevent it. You can sort of factor it in when you are practicing with a target. Okay, let's get into 40. Guys, I'll tell you what. If it's a question on the arrow, we'll take it right now. If it's some overall question, let's just wait and finish this and take all the questions together. How's that? Yeah? Okay. All right. So let's just go ahead. We've seen these. Yeah. Is there a maximum weight of the arrow you can use in the Olympics? I don't know. I'll have to find out. I don't know. Good question. There must be. I mean,
I don't know it, but
there must be. There must be. I mean, honestly, you would not want too heavy an arrow either, or too light. So there must be some.
Plenty of questions about arrow.
Okay, we'll look at them.
Size, weight, specific geometry.
Yeah. These are all things which you should ask Google, Bob. Arrow. Yeah, go ahead. In shooting also, do you have to shoot at a higher angle because the bullet is going to fall back with gravity? In principle, yes, the thing depends on whether it is a 10-meter pistol shot, where 10 meters is such a close range that the effect is minimal, versus if you are doing some clay pigeon shooting, which is much at a higher distance, or if it is a rifle thing, which is at a much higher, longer distance, you will have to compensate for this. So many modern guns, you have sights, right? Not everybody is like this Turkish guy who just comes, puts a hand in his pocket and bindasly tuck shoots, and most modern guns have sights. So there's a crosshair that tells you approximately where the bullet might hit. Most of these crosshairs are compensated for the fact that if you can put your target in the crosshair, the bullet will probably go there. They're compensating for at a particular distance, they're compensating for the fall due to the gravity on the bullet. So you have sights which are compensated sights. Anything more about arrows? If not, let's finish this and then come back to it. Arrow, yeah. There are definitely different types of fletching used for different. I do not know the rules of archeries and arrows and fletching, but fletching is the arrangement of your feathers at the end to make your thing spin. Are there different types? I don't know the answer to that. I don't know. Okay, guys, wait. Let's finish this. Because otherwise, okay. Because chai will get cold if we don't finish. Okay, running. So there are two questions we can ask. The first one is sprinting. Why aren't you not running like Usain Bolt? Okay, but that is typically the fastest runners are running about 100 meters in 10 seconds. Okay. The other end is, why are you not running like Eliud Kipchoge, who is the marathon specialist, okay, which is running in 42 kilometers in about 2 hours. Okay, so both ends you have to worry about. So now running is a topic which has been studied to death. Okay, there are hundreds and hundreds of papers on this. In fact, just on Usain Bolt's run, there are hundreds of papers. There are blogs. There are proper papers in journals of multi-component velocity measurements for linear sprinting, Usain Bolt's world record analysis, etc. Physics of sprint. There are lots of papers. Right from the 1920s till today. There are lots and lots of papers. It's just a snapshot of them. I just want to highlight a few things. One name you find in a lot of old papers is A.V. Hill. Okay. Another name you'll find in a lot of 1970s papers is J.B. Keller. Okay. So these two guys are kind of the heroes of this field. It's worth looking at this. So the pioneer in looking at analyzing running is A.V. Hill, Archibald Vivian Hill. He received the 1922 Nobel Prize in Medicine or Physiology. For what? For his discovery relating to the production of heat in muscle. The fact that if you use your muscles, it's going to get warm. He got a Nobel Prize for that in 1922. And he came up with, if any of you run and or something, you'll know that there's something called VO2 max, the maximum amount of oxygen that you can use, which sort of defines your performance. He came up with this thing, and one of the questions he was asked is, why are you busy studying athletics? You could be doing more useful things like study industry, study disease, etc. Why athletics? And this was his answer. He said that the process of athletics are simple and measurable. You can measure things. You can measure how long people take to finish a standard race or something. Athletes themselves, being in a state of health and dynamic equilibrium, can be experimented on without danger. So he said most of these athletes are fit. You can ask them to run the same thing again and again. They don't mind. Okay. They are generally fit. So they can be experimented on without danger. And they repeat their performances exactly again and again. And the study of athletics and athletes is amusing to us and hopefully to them. Okay, which leads to a fourth reason, that being amusing, it may help to bring new and enthusiastic recruits to the study of physiology. So he wanted to get more people to study physiology of the human body, and he thought that this was good. If they find it's fun to work with athletes, it's cool, to do some experiments on guys who are running and jumping and all, maybe more people will join the field. So this was his. So because of Hill, he was such a dominant person. Early work, 1920s till the 1940s, 50s, etc. Even after the World War, most of the work done in analyzing running, jumping, all that is done by people studying physiology or medicine. Okay, not so much by physicists and mathematicians. This changes with Keller. Keller is a mathematician. Okay. Keller made it mathematical and he said, this is what I want to do. We wish to determine how a runner should vary his speed v, velocity, as a function of time during a race of distance d in order to finish it in the shortest time. So he has defined the problem for you mathematically. I have to run a distance d in the shortest time possible. What should be the change of my speed during the race? That's basically what he did. And he wrote many things based on it, and then people took over from there. Now, Keller is an amazing personality. Like Hill was, this guy is another thing. He's a well-known mathematician. He's a student of Courant, another very famous mathematician, the Courant Institute and all. Emeritus professor at Stanford. And he won 2 Ig Nobel prizes, not Nobel prizes, Ig Nobel prizes. Okay. What is an Ig Nobel prize? We'll come to later. Okay, ask me in the break. But Ig Nobel prizes are given to people who do fun research, which is interesting, but kind of, aisa bhi log karte hain kya? So, the first Ig Nobel he got was the second one actually here, which was, he studied ponytails and he wrote a paper. This is a paper in Journal of Applied Mathematics. Why does a jogger's ponytail sway side to side when her body is moving up and down? Okay, so this is when he got his first Ig Nobel prize. Okay.
There is no unanimous agreement to this.
What?
Why it really happened?
No, I think he's worked out the math. But then they figured, arey yaar, this guy does all kinds of hatke researches. He's been doing this all his life. So they gave him another, backdated Ig Nobel prize for work he had done in 1957. In 1957, now when you pour chai, just take a spoon and you're pouring chai, the last drop will stick to the spoon and fall. So if you ever use a teapot, you pour tea from a teapot, there's always that one drop stuck on the teapot. So he did a lot of analysis, Journal of Applied Physics, how tea falls off a curved surface, calculated the optimal curvature for the teapot spout to minimize that drip. So what should be the curvature of that? So they gave him, for the ponytail work, he got 1 Ig Nobel, and they said, to see great hope, we'll give you 1 more for this earlier work. Yaar, paper pad lo. I mean, don't ask me this, but this guy is a very, he's literally a very colorful character. Okay, he's passed away now, but anyway. So, Keller. Now, I cannot go into there are 100, it's very, very complex, but I'll give you the very simplistic idea. Okay. Now, if you are a runner, you have certain weight, your body has a certain weight, gravity is acting on you, so there is some force pulling you down. Okay. Now, you need to go in front, so which means you have to have some force in the forward direction, which is x, but also you need to push the ground to jump up. See the difference between running and walking. In walking, one leg is always in contact with the ground. In running, at a certain point, one leg is in the air. Okay, that's the difference. So you also have to get off the ground. So you need to push down so that you can lift off the ground. And you need a certain amount of friction to be able to push back so you go in front. Okay. Now, it's a little bit more complicated. Have you seen any of these guys, Usain Bolt, Asafa Powell, any of these runners? They have huge upper bodies. You need a lot of upper body strength to run. In fact, if you want to be a good runner, do lat pulls, exercise your deltoids, exercise your traps. These are the muscles that help you run. Apart from your legs, you need legs, of course, right? Because every time, remember, our legs are not in the center of the body. Our legs are at the side. So if I push back, whether it's the right leg or the right thing, there is going to be a torque. If I push back, it's not at the center, it's going to turn to twist you. So you need to move your arms to balance that, because otherwise this will turn you one way, you turn the other way with your hands. So you need these muscles to help you balance and keep you in front. Now people have done a lot of work about when you walk, how does your center of mass move, when you run, how does it move, what is the shape? People have done infinite work on this. Now what's the difference between you and Usain Bolt? Right? Are you in the air for more? Does he jump higher? Is he in the air for more time? No. Most of us will be in the air for the same time. His thing is the amount of pushback that he can do and the amount of force that he puts in front, the size of his stride and things like this. Now this is homework for all of you. So this is a table comparing Usain Bolt, the 9.58 run, with the rest of the finalists in that race. Okay, there are two things to look, a couple of things. The step, how the number of steps, he took 41 steps to cover 100 meters. 41 steps to cover 100 meters. The other people took about 45 plus minus something. Okay, so 4 steps less. I want you to do this. 100 meters is a distance which you approximately know 100 meters a stadium or something, right? And 100 meters, I think all of you can walk or run 100 meters without dying. Okay, so what you should do is walk 100 meters, run 100 meters. See how many steps you take. Usain Bolt does it in 41 steps. 21 with the right leg, 20 with the left leg, right? Distance for each thing is 2.5 meters. And you would think that a lighter person would be able to run quicker. He's actually, compared to the other athletes, much heavier. Okay. Because of which, if you're heavy, remember, force is mass times acceleration. If you're for the same force, if you're heavier, the acceleration is less. But he has enormous strength in his legs. He gets a lot of acceleration in the beginning. And then if you remember in one of the races, even like 10 meters before he raised his hand in victory, he is so heavy, inertia, Newton's first law, he will just keep going. Once he has reached that speed, he just keeps going. So that is where so after about 70 meters, his weight is helping him. It is just inertia taking him ahead. Even if his muscles are tiring, he's going to keep going once he's got that speed. Okay, so go home, do this. Okay, you don't have to tell anybody else your results. Right? Don't tell anybody else, but just figure out how many steps you need to cover 100 meters, and from that you can figure out your average step length. Hey, this guy's dead. Yeah, this guy's, forget it. I can do it from, I mean, if this works, it's fine. We don't need the pointer. But just figure out this. This is very interesting. Okay, because the amount of time in the air, it's not that he's jumping much higher than everybody else. 0.12 second or something, that's about the same for everyone. Now, at the other end, endurance running is completely different. If you want to run for a marathon, 42 kilometers, okay, that is completely different. The parameters to be optimized are very different. If you see marathon runners, they are not these huge guys. They are thin guys, right? You wonder, like, where are they? Where is their muscles? You know, one thing, but no, their thing is endurance. And remember, one of the dreams in marathon running has to be break the 2-hour thing. Can you run a marathon in 2 hours or less than 2 hours? And it started off by this Nike's thing called Breaking 2. Breaking 2 2017, they had this race on the Monza, it was a car racing track in Italy. They had chosen 3 runners, Kipchoge, Tadasi, one from Kenya, Ethiopia, and Eritrea. And this got the news because of the shoes they were using. Nike had come up with these Vaporfly Elite shoes, and most of the press that this got, I mean, he managed to get 2 hours 25 seconds, not accepted, of course, because this was a special track and they had special pacers, etc., etc. But this got into the news simply because of these shoes, okay, and the rules that are there for shoes. And after this race, the IAAF, the international body that controls athletics, changed the rules for shoes. Okay, and so now the rules say this, that the shoe must not contain more than one rigid embedded plate or blade of any material that runs through the shoe. So the idea is this: every time I come down, if I'm running, every time I come down, the shoe bends a little bit, right? So can I store that energy and release it like a spring? And essentially they are saying no springs. You cannot use your shoe to store energy and give it back to you on your thing. So they should be, you can have one plate. So there are some plates put to make the thing firm, because these shoes are very thin. You want something to make it firm. So one plate is allowed, but nothing that will store energy. And any shoe must be available for purchase by any athlete on the open market. You can't have a specially designed shoe that's only for me and nobody else in the world has it. I won't sell it to anybody else. So it has to be an openly available shoe for at least 4 months before the competition. That's what they said. These are the new rules. Of course, they were not content because 2 hours, 25 seconds is not the same as 2 hours. After this is when Kipchoge is at his peak. He broke the world record at the Berlin Marathon in 2018. I was there in that race. Yes, I ran a race in which a world record was set. Okay. Now, of course, let me tell you this. Hang on. So the Berlin Marathon is amazing. 40,000 people run. The elites, they start them in batches. So people who are absolute elites will start first. Then after 10 minutes, they start the next set. Then they start the next set. So Aam Janta like us will start almost an hour later. Okay. So by the time we started, he had already crossed the halfway point. And we knew that, everybody had said it's going to be a world record because he had already cracked the point at which he should have been at 21 kilometers. It was 1 hour, 1 minute. It was 1 hour, 1 minute when he crossed 21 kilometers and we had not yet started the race. And then, so they were announcing that he's already crossed something. It was crazy. He did 2 hours, 1 minute something. His first 21 kilometers were slower than the next 21 kilometers. Okay, anyway, but that's Kipchoge. So after this, they had finally this thing called the Ineos 159 challenge to do it in less than 2 hours. This happened in Vienna in 2019, and this is essentially a run designed by computer. Okay, so there were totally 41 pacemakers. Rules allow you to have max 2 or 3, depending on the race. They had done trials in wind tunnels and simulations to show that if these are so these are 5 guys making a V, there is 1 person, this is the runner, and there are 2 guys behind. These behind guys also help this guy get some speed. Okay, so this is the thing. There are 5 guys here, Kipchoge, 2 guys behind. This is the position for minimum wind resistance for the runner. This apparently calculation showed saves 4 minutes of running time at that speed. Okay, then they had laser guided pacing. So the problem with pacers is they need to know, are we on target or not? So they have to look at their watch. Are we on target or not? Here, there is a car in front of them that is giving 2 spots for the first runner and the last runner where they should be at that time, because the whole path is calculated. So they know that they just have to follow that light. And I mean, clearly Kipchoge is trying to run it in 2 hours or less than that. Nobody else will be able to do it. So people are joining the race as pacers, tiring out, leaving. New set of people come, they tire out, leave, so that they can be faster than him. Okay, so they were running only for short distance, and that's why they need 41 pacemakers. They chose a place in Vienna which has a lot of trees, an avenue which has trees on both sides. So for a year, they went around various cities measuring the wind speed. This is one place they found with an average wind speed less than 1 meter per second. So they said, we'll do it there. There's no crosswind. There was something to provide. Normally in the marathon, there are some water stations where you can go and pick up a drink. Here, they was giving continuous hydration along the path. So because of all this, is not recognized by the IAAF, but still he did it in 1:59:40. He broke the 2 hour limit. This is, just imagine, this is an average speed of more than 21 kilometers an hour. You cannot do that in Mumbai with any vehicle you have. Right? I mean, this is just the kind of endurance you have in this is fantastic. Anyway, coming to the running, there is, on one end, you have all these fancy shoes and all. On the other hand, this is the original person who changed marathon running, Abibi Bikila. 1960s, consecutive Olympics, gold medals. Nobody thought this guy had come from somewhere in Africa, didn't have shoes. He ran barefoot and he won. Okay, and this started off a trend in barefoot running. You can ask me more about this. Is something I know a little bit about. The whole thing is, when you wear shoes and when you don't wear shoes, if you wear shoes, you will strike on your heel. Okay, when you strike on your heel with shoes, you send a shock through your entire leg and hence through the spine and everything else. When you do not wear shoes naturally, right, you tend to strike more on the middle or the front of the leg. It's much more, your leg itself behaves like a spring to absorb most of the shock. Okay, so Humans were designed to run. In all our evolution, before we figured out shoes, we ran, right? And we ran barefoot. We are designed to run barefoot. That's the philosophy, that it's much less stressful on the body. So there are, of course, today you have shoes with all kind of gel and this and that to protect you, but this was a big thing. Now, if you're jumping, your shoe is very important. So in 1957, there was this guy Stepanov. He set a world record in the high jump. He had a 4-centimeter heel. 4 centimeters is this much. Iska heel itna tha, shoe ka. I mean, sports shoes. Sports shoes with this much heel. Obviously, he gets an advantage. After that, they made the rules. Immediately, 1958, the rule was changed that you can't have more than 1.3 centimeters. 13 millimeters is the maximum sole that you can have. Now, remember, that's for the high jump, where clearly any height increase is an advantage. But in long jump, every 1 centimeter increase in height, you go 2 centimeters further. So this is also important for something. So you have the same height restrictions also for long jump. But for long jump, people are smart. Have you seen a long jump? You run, there's a takeoff point, you jump and you land in the sand somewhere. And the last part you land, so even if your hands are at the back, that's where they'll count. But people will keep their hands in front and they'll somehow land with their shoes. So what have people started doing? They have what are called negative heel shoes. What's a negative heel shoe? I couldn't find a picture, so I just drew this. But basically, this is a normal shoe, right? You make a shoe like this. So when you land on the heel, when you land like this, they'll count from here. So you generate these 2-3 centimeters extra you got. Huh? Well, it's the height, the restriction is on the height of your sole, not the shape of your shoe. No, this is still, you can still do this. I mean, remember, you can't do much of it, right? Because eventually you can't just knock off the, I mean, so. Now, what if you didn't have legs? Okay. So, this is Oscar Pistorius, very in the news for all the wrong reasons, effectively. But he was amputated, he had no legs, he had these artificial prosthetic things, which are made from carbon fibers. Now, this also got into a lot of controversy because remember, these things can flex and store energy. Can this give you an unfair advantage over somebody with a leg? Because legs have weight. You have muscles and bones and everything. Legs have weight. This can be very lightweight. This can swing. The amount of time it is in touch with the ground, etc., you can maybe change. Eventually, they figured out that there are some designs which are okay. They don't offer you any advantage. But this got into a lot of things that, can you design something where a person without legs with these artificial things is actually faster than somebody just because of the advantage they're getting from these devices. So, again, this is a lot of modeling, simulation, etc., which you can do these days. Okay, it's an hour. I can stop here. Otherwise, if you'd like to know, I can very quickly tell you about the pole vault and diving, 2 things which I have not talked about. I will go through this. No, we won't go through very much details, but pole vault is an example of energy conservation. It's an entirely energy conservation. And if you see, again, the pole is very important. So a pole can be any material, any length, any diameter. There's nothing stopping you from what is a pole. Okay. Now, what's the best material for a pole? What do you want to do? How do you do a pole vault? You catch the pole, you run with it, you jam it into somewhere. The pole bends. So your energy which you had while running, kinetic energy, is now transformed into elastic energy which is stored in that bent thing. Now that bent pole is going to go back straight and you're going to go up with the pole and hopefully above the bar. Okay, that's the energy transfer that's happening. So you must return that stored energy at the right time. Ideally, the pole recoil, the straightening up, is finishing exactly at the peak of the thing. And it must minimize the shock when you do it, because otherwise, if it's a sudden shock, you'll just fall off the pole. So you can, it depends on what it is, the length, stiffness, it depends on your style, whatever else. Typically, it's about 5 meters for men. And it turns out that one of the best materials for this has been bamboo, which is what people use to jump over fences and all this thing, bamboo. Bamboo bends well, bamboo has a lot of strength, it can store energy, it's very well. Of course, then people have got it much better now. These days, it is hollow fiberglass and you can play with it. Please remember that, I don't know if you've ever carried a pole, any pole. okay, a block of a wooden, thing. Carrying it into the middle is very easy. Carrying it not in the middle is very difficult because it's going to tend to bend down. You see pole vaulters, they have massive upper arms. They have to carry it. The pole is not held at the center of gravity of the thing. You hold it at the side. These days, they make poles which have a different mass distribution along the length. Okay, you can model all this. You can have some amount of stress built into the pole so that it will bend in a particular direction once it is jammed in. You can watch some videos later. Swimming. So just remember, typically running speeds are about 5 times faster than swimming speeds for the same distance. So you can compare. You can compare 400-meter running approximately with 100-meter swimming. Okay, and if you look at the thing, in the same period, 400-meter running goes from 44 seconds to about 43 point something, less than a second. But whereas 100-meter freestyle goes from almost 52 seconds to almost 5 seconds difference here. And at least until recently, it appeared that swimming records were being broken more frequently. And this is one case where it was entirely up to because of new age swimsuits and new materials and computer-aided modeling and wind tunnel testing and all which was happening. I'll come to all your questions. Let me just finish this. Now they have stopped all this. They've given some rules which make it very difficult for you to come these fancy materials. Last example of physics is diving. Okay. Now in diving, for a long time, what is it? It's a plank. You must have done this in a classroom. You've taken a ruler, put it at the edge of the desk, pull it down, leave it. It goes. You keep a rubber on it, it will go fly away. You've done this. Exactly the same thing. This is what is a cantilever. Now earlier there were wooden planks. Now there is a guy in 1949. He's working at an aircraft company which you all know called Boeing in Seattle. So he's working on Boeing on aluminum alloys which they use for making aircraft. And he says that why don't I make a diving board out of this? So he starts a company to make diving boards, and these are aluminum alloys. And now you find these diving boards which have, earlier it is just fixed here and now it is fixed here. That end is free. So you can control some amount of the tension this as well. But the modern diving board is a complete thing of physics and modeling. Okay, it has some very fancy material. It is tapered, so that the thickness also varies along with the length. And at the tip of the board over here, there are holes. These holes do many things. One, the diver is going to be wet and coming there, it allows the water to go through. So the thing remains dry because the water can drip through it. But it decreases the weight at the tip. So now it's not a uniform piece of metal. It's a piece of metal whose weight per unit length differs along it. You can use it to maximize the lift that you get at one end. Okay. And because of this, see, normally if you have a piece of wood, whatever, it's going through the air, there's air resistance. Now the air can go through it. So it changes the air resistance also. That also helps you get extra lift. Because of these modern diving boards, you get huge amount of lift and performance compared to what you can do earlier. And hence you can go up and then do all kinds of twists, turns, whatever else. Design of the diving board, all due to physics and modeling. Okay. So, the Olympics are a big inspiration for me. And just remember that in today's world where a few millimeters or a few meters per second makes a difference between winning or losing, you don't win silver, you lose gold, right? Makes a winning or this thing. Physics is very important, right? That's the Indian team on the boat going by. I just hope they do well. Most of the important events are still to come, so I think there's hope. But just remember, the fact that they've qualified for the Olympics itself, I think, is amazing. Our performance is going up slowly. We come from a, we don't have a real sporting culture, right? I mean, the office chair is the next cigarette. It's making us lazy. It's making us not be active. So, take the inspiration from this, be active, and you can ask a lot of questions. So I'll stop here. It's just about an hour. So we'll take a few questions here. We'll take online questions and we'll stop the live stream. You guys are here. You guys get your chai and you guys can ask all the questions in the next hour. No problem. So first, let's take the online questions.
Most of the questions are already.
Okay. Are there new questions? No. Okay, let's take 1 or 2 questions here and then break for chai, and then we'll come back and have the rest. Yes, any urgent questions?
Actually, there's a very funny.
Okay, there's an interest.
See, recently, ACs were sent from India to Paris for the players. So, are they really required? It's true. Our people sent ACs. So, the question is.
I suppose it's very hot in Paris right now, so maybe if they need a good night's sleep, they need some ACs. Who knows? I don't know.
I think that's the concern. Europe has become very
It's become very hot. Okay, let's take 1 question. Let's break for chai after that, and then you can stop the live stream. Yeah.
How does doping affect the performance of athletes?
Not concerned physics. I'll take this later. Let's get one which is. Yeah. What is velocity? Velocity is just speed in a particular direction. Okay, so right now it is speed, because on a track there's only one direction. There's the chance that you're running the other way is very low. Yes, another quick question. Yes. That's typically a discus or a shot put. If you throw something heavy and round. Okay, I think you're discussing the hammer throw. Okay, so in a hammer throw, you pick up a hammer basically, and you want to throw it as far as you can. And even in a shot put, you will see they actually turn around a few times. They don't just pick it up and throw it. They actually turn around a few times and then throw it. Okay. Similarly for the hammer throw. Why? Why do they spin and then throw it? Very good question. Excellent question. Why do you spin and throw? Now, if you want control, okay, now remember you can't just throw it anywhere. You want to throw it within a certain cone. There's typically an angle. You have to throw it within that, right? And you don't want your thing to just fly around anywhere you're going. So something which is spinning has much more control in where it is going to go than something which is not spinning. Also, see, you have very little space in that area. The person can't, like in a javelin, you run, and then you can throw it. But here you can't run and then throw the ball. So how do you pick up some speed? The only way you can pick up by speed is by moving around and then making it as fast as you can, moving around and then releasing. That's one of the main reasons. That causes more? Not pressure. It just increases the speed at which you can release the object. Okay, I think we should break for chai. It's 12:15-ish now. Chai will get cold. Let's come back here in 10 minutes and then you can ask me all the questions you want. No problem. I don't guarantee I have answers to them, but you can ask me the questions. Okay, for the online audience, just remember our next session 2 weeks from now, stop the screen sharing. Yeah, let me just stop screen sharing just a sec. So online audience, our next session 2 weeks from now is at Ruparel College, and it is going to be on proteins. It's a chemistry talk on proteins. And a month from now over here, we're going to be back with the Ice Cube Neutrino Observatory at the South Pole. Okay, so those are the next 2 things coming up. You can write to us, outreach@tifr.res.in, or follow us on Facebook or Twitter or things like this, and you'll know about our latest programs.